Hello everyone, I'm Dr. Anupriya, Assistant Professor in Department of Applied Science and Humanities, associated with ABES Engineering College, Ghaziabad. In this lecture, we will discuss about spectroscopic technique and applications. Basically, we will discuss the elementary idea and simple application of UV-visible spectroscopy. And the topic we are going to cover basic introduction of spectroscopy, fundamental and instrumentation of UV-visible spectroscopy, and the application of UV-visible spectroscopy. Let me consider what is the spectroscopy. It is a branch of science that deal with the study of interaction of matter with electromagnetic radiation. That means when electromagnetic radiation interact with a sample, they change their energy via absorption and emission, and the spectroscopy is a powerful tool that study these energy changes and give the information in the form of spectrum. And what is the electromagnetic radiation? Electromagnetic radiation is a flow of energy which propagates in space and medium with their electrical and magnetic field. They have energy in the form of photon, which is equals to the E equal to h nu. H is a Planck constant and nu is the frequency of radiations. Electromagnetic radiation consists different number of radiation with different frequencies. When we arrange these radiation in increasing order of wavelength and decreasing order of frequency, we get a electronic spectrum, which consists gamma rays, X-rays, UV rays, I rays, and radio wave. Here, gamma ray have the high frequency and radio wave have the low frequency in all of them. And a small region have a range 400 nanometer to 700 nanometer is known as visible region because this region is visible to the human eyes. And ultraviolet region is like longer wavelength to the X-ray and shorter wavelength to the infrared radiations. Generally, the principle of spectroscopy is based on the measurement of spectrum of sample containing atom and molecules. And what is the spectrum? Spectrum is a graph between intensity of absorbed or emitting radiation versus wavelength and frequency of radiations. And it's come like this. On the basis of interaction of radiation, spectrum also two types, absorption spectrum and emission spectrum. When molecules exist in their ground state, after the absorption of radiation, they get excited into the excited state. This type of spectrum is known as absorption spectrum. When molecules already exist in their ground excited state and after the loss of radiation, they come back to their ground state, this type of spectrum is known as emission spectrum. So, on the basis of spectroscopy also two types, absorption spectroscopy and emission spectroscopy. Absorption spectroscopy work on the absorption of radiation. For example, UV-visible spectroscopy, IR spectroscopy, etc. Emission spectroscopy is work on the dispersion of radiations. For example, mass spectroscopy. Now we will discuss how the molecules interact with electromagnetic radiation and how they change their energy and how we can record this energy in the form of spectrum. We know that when molecules interact with the electromagnetic radiation, they change their energy via translation, via rotational, via vibration, and via electronic transition. The energy change by translation is very low. It is negligible in molecular spectroscopy. When molecules absorb the energy which is sufficient only for the rotation of molecules, they change their rotation level R1 to R2. And these energy changes we record as rotational spectra and it is observed in microwave and far IR region. When molecules absorb the radiation, which is enough for rotation as well as vibration, the energy change, molecule change their energy via vibrational level, and these energy changes recorded as a vibration spectrum, and it is observed in higher region. When molecule absorb that much energy which is sufficient for the excitation of electron from ground state to excited state, and these states contain rotational energy level as well as vibrational energy. These changes is recorded in the form of electronic spectrum, and this is observed in UV visible region. Now we will discuss what is the UV visible spectroscopy and how it works. It is also known as electronic spectroscopy due to the electronic transition. UV spectroscopy. UV spectroscopy is concerned with the study of absorption of UV radiation, which ranges 200 to 400 nanometer, and visible region extend from 400 to 800 nanometer. Valence electron absorb the energy, thereby molecules undergo transition from ground state to excited state, and this absorption is characteristic and depend on the nature of the electron present. That means UV visible spectroscopy is work on the molecule should absorb UV radiation, and after the absorption of UV radiation, the electron present in the ground state excite to the excited state, and these energy changes record in the form of spectrum in visible spectroscopy, and this absorption is characteristic and depend on the nature of the electron. For example, they have sigma electron and pi electron. The spectrum is based on the nature of the electron present in a molecules. And the instrumentation of UV visible spectroscopy consists source of radiation, monochromator, sample compartment, detector, and recorder. Generally, deuterium lamp and tungsten lamp are used for the source of UV radiation. After the filtration, monochromator give a specific range of radiation, and these radiation pass through a sample and reference. The detector detects how much energy is absorbed by the sample, and recorder give the information in the form of spectrum. Here we can see that when we record the UV visible spectroscopy, we dissolve our compound in a solvent. It can be polar and non-polar. And the monochromatic radiation pass through the sample. The sample absorbs some radiation and this radiation, how much is absorbed by the sample is detected by detector and give the information in the form of spectrum. Absorption, we know that when a radiation interact with a matter, some amount of radiation is absorbed by the matter and some amount of radiation is transmitted and some amount of radiation is reflected. When a sample is absorbed the radiation, they follow some absorption law which is known as Beer-Lambert law. According to this law, the absorbance when a monochromatic radiation is passed through a sample, the decrease in the intensity of radiation is proportional to the thickness of sample and the concentration of sample. That means the absorbance is directly proportional to the concentration of sample and the thickness of the sample. So A absorbance equals to the epsilon CL. This is known as Beer-Lambert law. A is the absorbance, epsilon is the absorptivity coefficient, C concentration, and L is the path length of absorbance solution. By the Beer-Lambert law, we can also calculate the molar absorptivity coefficient if we use a molar concentration. By the dividing of molar mass of concentration, we can calculate the molar concentration of sample. And the transmittance is a ratio of transmitted radiation to incident radiation. So the absorbance is the logarithm of reciprocal of transmittance. Based on the Beer-Lambert law, we can solve some numerical problems. Here, the molecular absorption coefficient of tyrosine in water is 1280 per mole centimeter at 280 nanometer. Calculate the concentration of tyrosine solution in water if the absorbance of the solution is 0.34 in a 1 centimeter path length cell. That means what is the given? Absorption coefficient is given, path length is given, and absorbance is given. What we have to calculate? The concentration of solution. So according to the Baeyer-Lambert law, absorbance is equals to the molar absorptivity coefficient, concentration, and the path length. So concentration is equals to the absorbance divided by molar absorptivity into path length. After the putting all the value, we get the molar concentration of solution 250 micromole. Another example, a compound having concentration 10 to the power minus 3 gram per liter, relative absolute value is 0.20 at lambda max 510 nanometer using the 1 centimeter cell. Calculate its absorptivity and molar absorptivity value. Given molecular weight of the compound is 400. What given? Concentration of the compound is given 10 to the power minus 3 gram per liter. Absorbance is given and the path length is given. We have to calculate the absorptivity. First, we calculate the absorptivity coefficient, which is equal to the absorbance divided by concentration and path length. And we get the absorptivity coefficient 200 liter per gram centimeter. We know that for calculate the molar absorptivity coefficient, we have to calculate the molar concentration by dividing the concentration with molar mass. Molar mass is already given 400. Then we divide the concentration 10 to the power minus 3 gram per liter to 400. We get the molar concentration 0.25 to 10 to the power minus 5 mole per liter. So now the molar absorptivity coefficient equals to the absorbance divided by molar concentration and path length. So molar concentration is equals to the 8 into 10 to the power 4 liter per mole centimeter. Now we will discuss the possible electronic transition in a molecules. We know that according to the molecular orbital diagram, molecules have bonding, non-bonding, and anti-bonding state. On the basis of the nature of the electron present in a molecules, the transition are 4 types: sigma to sigma star transition, pi to pi star transition, non-bonding to sigma star transition, and non-bonding to pi star transition. Sigma to sigma star transition generally observed in the saturated compound which have only sigma bond. An electron from sigma orbital is excited to the corresponding anti-bonding orbitals. This transition is a high energy process lying in the vacuum UV region. For example, methane CH4, which have 4 sigma bonds, undergo sigma to sigma star transition show the absorbance maxima at 125 nanometer. Pi to pi star transition, this type of transition generally observed in the compound which have multiple bonds. For example, alkene, alkyne, carbonyl, nitrile, and aromatic compound undergo this type of transition because they have the pi electron. For example, alkene generally observed in the region of 170 to 200 nanometer. Aliphatic ketone, a bond bend around 185 nanometer arise due to the pi to pi star transition in the carbonyl group. Non-bonding to pi star transition. This type of transition is observed in the molecules which have double bond with involving heteroatom because they have the non-bonding electron. An electron from non-bonding orbital is promoted to the anti-bonding pi star orbitals, and non-bonding to pi star transition require minimum energy and show the absorption at longer wavelength around 300 nanometer. And to sigma star transition, this type of transition generally observed in saturated halide because they have the non-bonding electron and sigma electron. An electron from non-bonding orbital is promoted to the anti-bonding sigma star orbital. Sigma to pi star transition and pi to sigma star transition are forbidden transition because they not follow the selection rule. They are theoretically possible, practically they are not possible. And what is the selection rule? When electron excite from ground state to the excited state, they should have the same spin. If electron have the minus half spin in ground state, it should have minus half spin in the excited state. If they have plus half spin in the ground state, they should have plus half in excited state. So the overall delta is 0. According to the energy, sigma to sigma star have high energy, then non-bonding to sigma star, then pi to pi star, then non-bonding to pi star. Sigma to sigma star and N to sigma star are the high energy. That means they observe at shorter wavelength and which are not observed in UV region. We know that the UV region is 400 to 200 to 400 nanometer, and this transition is not observed in this region. Only pi to pi star and N to pi star transition are observed in UV region, so that all the unsaturated compounds which have pi bond are known as UV active compounds. There are some specific terms which is used in UV-visible spectroscopy: chromophore, oxochrome. Chromophore is a part of molecules which is responsible for the absorption of radiation as well as color of the compound. That means chromophore are the part of the molecules which absorb the UV radiations and get excited from ground state to the excited state. There are some functional groups containing multiple are capable of absorbing radiation about 200 nanometer due to the non-bonding to pi star and pi to pi transition. For example, nitro group, carbonyl, cyno, and double bond. Oxochrome, oxochrome that part of molecules which are individually does not absorb the UV radiation, but when we attach with chromophore, they alter the wavelength and intensity of absorption of chromophore. For example, benzene have a lambda max approx 255 nanometer. When we attach phenol OH group, the lambda max increase near about 270. When we attach aniline, the lambda max increase approx 280 nanometer. That means OH and NH2 group are known as oxochrome. Bathochromic shift. When absorption maxima of a compound shift to longer wavelength in a spectrum, if lambda max is shift to the longer wavelength is known as bathochromic shift. And this effect is due to the presence of oxochrome, which increase the conjugation or by the change of solvent. For example, in a paranitrophenol, so the absorption maxima at 255 nanometer. When we decode this absorption maxima in alkaline medium, the absorption maxima is to the longer wavelength because the negatively charged oxygen delocalize more effectively than the unsafe pair of electrons. That means in alkaline medium, the absorption maxima show the bathochromic shift. Hypsochromic shift, if the absorption maxima shift to the shorter wavelength is known as hypsochromic shift. For example, aniline give a lambda max at 280 nanometer. When we decode in alkaline medium, in acidic medium, benzenium chloride is formed, which hinder the conjugation of to benzene and show the lambda max at shorter wavelength. This is known as hypsochromic shift or blue shift. When the intensity of lambda max increase is known as hyperchromic shift. For example, in butadiene, the absorption intensity is 21,000. When we introduce oxochrome methyl, the intensity increased by 400. And hypochromic shift, when intensity is decreased, is known as the hypochromic shift. For example, biphenyl show the intensity at 19,000. When we introduce methyl group at the ortho position, they hindered the conjugation and the absorption intensity also decreased to 10,000. This is known the hypochromic shift. Overall summary is that when lambda max shift to the longer wavelength is known as red shift, lambda max shift to the shorter wavelength is known as blue shift, intensity of the absorbance is increased is known as hyperchromic shift, if intensity of the absorbance is decreased is known as hypochromic shift. There are some factors which are responsible for the shifting of absorption maximum. First is conjugation. As the conjugation in the molecules increase, the band gap of the molecules decrease. A band gap decrease, we know that the energy is inversely proportional to the lambda. That to energy increase, the lambda max decrease. So that these molecules show the bathochromic shift. Here, ethylene show the, for example, ethylene show the pi to pi star transition when the increase, the band gap decrease, when the conjugation increase, band gap decrease, and these are show the bathochromic shift. Oxochrome, when oxochrome increase the conjugation, so the bathochromic shift. For example, benzene has a lambda max at 250 nanometer. When we attach the phenol OH group, so the bathochromic shift, when we attach the antimony, it is always for the bathochromic shift due to the increase in the conjugations. Next is solvent effect. We know that when we decode the UV visible spectra of a compound, we dissolve it in a solvent. It can be non-polar and polar. It can be non-polar and polar. When our molecules is non-polar, then there is a no significant effect of polarity of solvent. But if our compound is polar, the polarity of the solvent play a important role for the absorption maxima. Generally, the polarity of solvent affect the pi to pi star transition and N to pi star transition. Here we can see that when we decode the spectrum, there is a transition pi to pi star. When this spectrum we decode in more polar solvent, the pi star transition is stabilized. That means the band gap between pi to pi star is decreased. Band gap decrease, that means lambda max increase. So that this type of transition show the bathochromic shift with increasing the polarity of solvent. When the molecules show the transition N to pi star transition, we decode in the polar solvent the non-bonding state is stabilized in more polar solvent. So that the band gap between non-bonding to pi star is increased. Band gap increase, that means lambda max decrease. This type of transition show the hypsochromic shift in more polar solvent. So finally, the conjugation, oxochrome and solvent play a important role for the shifting of the absorption maximum of compounds. There is an application of UV-Visible Spectroscopy by the Beer-Lambert law. We can analyze the qualitative and quantitative analysis of samples. It is used for characterization of aromatic compound and conjugated olefins because of conjugated and aromatic compound show the bathochromic shift. It can be used to find out the molar concentration By the Bayer-Lambert level, we can calculate the molar concentration of solvent. Detection of impurities. Then we discuss the spectrum of a sample. So another peak is observed in the spectrum. We can conclude that there is some impurity present in our sample. For every sample have a characteristic spectrum. If these characteristics does not match with the given recorded spectra, that means our sample is having impurities. Detection of function group. Every function group have a characteristic spectra. Detection of isomer are possible. By the UV-visible spectroscopy, we can detect the cis and trans isomer because in cis molecule, the conjugation steric is hindrance and conjugation is decrease. So that the trans molecules always show the bathochromic shift compared to the cis isomer. This is overall from my side. Hopefully, this will be beneficial for